Hello, my name is Roy Simpson, professor of mathematics at Columbus River College in Sacramento, California. In this video, we're going to talk about how to use technology to do numerical integration. I am assuming that you have been exposed to numerical integration techniques prior to watching this video. And I should tell you that really there's three reasons why you would do numerical integration. The first being that it's part of a curriculum, usually for an introductory calculus course. So usually you run into like the left endpoint method or the right endpoint or the midpoint method in your Calculus 1 course. And then you run into trapezoidal rule and Simpsons rule in your Calc 2 course. And there are a lot of other methods for numerical integration out there, but those are the base methods that you learn. And so that's the very first reason. It's just part of the curriculum. The second reason is that, and this is the more common reason, is that you're trying to integrate a function like this guy over here. And the function's terribly difficult to integrate or possibly impossible. Sorry, I used those two words together. So it could be that it is impossible to integrate that analytically, so by hand. So maybe you, because of that, you'll want to resort to using approximation techniques, which is called numerical integration. Lastly, you could be just given a list of data points like this, and you might be asked to find, let's say, the area underneath that curve for some reason, or maybe sum up some type of probabilistic entity that occurs with this data. So what you want to do is use some type of numerical integration technique to do this. And there are, like I said, quite a few that exist. All the methods kind of center around the same two formulas, which is that we slice up the interval, like in this case from 1 to 8.1 pi, into n slices, and the width of each slice will be average, or will be the same. So delta x is the width of the slice, and that's just b minus a over n, and you should recall that from Calc 1. And then additionally, you label your n plus 1 points, technically speaking, because you're starting at x sub 0 and going to x sub n. You label them as x sub I is equal to a plus I delta x. And then you basically use some type of geometry to help you find the areas of either rectangles or trapezoids underneath the curve. And so, for example, the right endpoint method, dragging this on up, looks like this, right? So to use the right endpoints within intervals, within the first interval, we're going to use the x sub I, or the rightmost point, because the leftmost point of the first interval is x sub 0, right? And so that would be height times width, so that's just a rectangle. And then you have the left endpoint method, which means that, let's say in our first slice again, you're going to use f evaluated at x sub 1 minus 1, or x sub 0, the left endpoint of that interval, to approximate the height of that rectangle, and so on and so forth. And then we do the midpoint method. And the purpose of the midpoint method is basically within the, let's say, the first interval, you're going to take the average x value, which is a sum of the endpoints divided by 2. That's the average x value in that interval. And you'll use that to approximate the y value. So you'll average out the x values, plug that into the function, and it gives you what we would say is the averaged y value. It's actually not the averaged y value. It's the y value approximated at or evaluated at the average x value in the interval. And then you grow into, now these are all Calc 1 concepts, then you go into trapezoid rule. And I had to rearrange things a little bit here just so that we could kind of start fitting everything on the same screen. But the trapezoid rule is different slightly from the midpoint rule. The midpoint, you take the average x value and you use that to give you the approximate y value for your rectangle, the height of your rectangle. In the trapezoid rule, you're just finding the area of the trapezoid, which really averages the y values instead of the x values. So that's what you're seeing here is the average of the y value evaluated at, or the y value at x minus 1, x sub I minus 1 versus the y value at x sub I. So you average those out and multiply those by the width, and that gives you the area of the trapezoid. Now, this is actually the first of the closed form methods here where you can have a better view of the formula by not writing it with summation notation, but instead multiplying it out. You should have seen this in your calculus class, so your calculus instructor should have shown you the result of this, but I'm going to go ahead and pause this video and type out the result. And it kind of bleeds off the page, so let me move over a little bit. All right, so in this case, you see the closed form. All I did was factor out a delta x over 2. And like I said, your instructor in your Calc 2 class should have showed you what this is, that you get this nice form for it. The endpoints f of x sub 0 and f of x sub n only occur once in that summation, whereas everything else occurs twice. And so that is the formula for the trapezoid rule. And then finally, and I'm going to scroll over to the right to include this, we have Simpsons Rule. And so again, there'll be a closed form for this. So let me make some space. And Simpsons Rule, like I said, is a bit difficult to write in a nice clean form because it is such a long formula, but it's a delta x over 3. Again, this should have been proven in your Calc 2 course. And it kind of has the same feel as a trapezoid rule. If you look at the trapezoid rule, instead of a delta x over 3, it's a delta x over 2. But then the trapezoid rule has f of x sub 0 plus 2 of everything else all the way till the end, which is just 1 of f of x sub n. Whereas Simpsons Rule is kind of like that, except it's over 3. And the first and last still has coefficients of 1, but then there's an alternation of 4 and 2. So 4, 2, 4, 2, 4, 2, and so on and so forth, all the way until it ends with a 4 and then the 1 at the very end. To use Simpsons Rule, n must be even. All right. So now the point of this video is not to rehash any of that or anything, but to show you how you could use technology to approximate the value of a given integral. So let's go ahead and start this problem. Now, to be able to use Simpsons Rule, again, n must be even. So I'm going to start by saying, let's go ahead and allow n to be an even number. Let's say 20. We'll do 20 slices here. Well, actually, that's a long interval. Let's do 50 slices. And all I did there was just go ahead and type in one cell n equals and then typed 50 in the other. The reason why I didn't type n equals 50 all into a single cell is because I want to reference that number 50. And so I'd like it to be alone by itself. And then I'll type in the values of a and b just in case later on somebody wants us to change these values. So I'll type in a equals and then tab over and I'll say 1. And I'll type here b is equal to space tab over and then I'll say 8.1 pi. Now, when I type 8.1 pi, I'm going to allow the computer to approximate this. So again, the whole point of this video is to kind of educate you on using something like Excel or Google Sheets to do something like this for you. So to do that, you always type equals 8.1 times and then pi. And unfortunately in Excel, you can't just type pi. That would be wrong. Even though it comes up like that, if I hit enter, it would give me an error. Pi is a function, so you have to put parentheses before and after, and now it'll actually approximate that for me. And just for cleanliness, I'm going to right align those A's and B's there just to keep it kind of nice. The next thing I'm going to do is allow the computer to compute delta x for me. So I'll type in here delta x. I know that's kind of silly typing it like that, but oh well. And I know that delta x is just b minus a over n. So now is one of the first times where I'm actually allowing the computer to do quite a bit for me. So I'll say equals, start the parenthesis for the numerator, click here, that's the b value, minus click here, that's the a value, end the parenthesis, and divide by n, which is that guy right there. Okay, and that works the same in Google Sheets as it does here. So that is our delta x. Right? And what's nice about this is if you choose to change n, maybe n to become 40, and hit enter, that will change for me as well. But I'll keep that as 50. Okay? And I'm a firm believer that technology, learning something like a spreadsheet package like this is incredibly important. And so you should want to do this. All right, I'm going to actually go ahead and maybe highlight these so I can see them as I move forward in my work here. And next thing I'm going to need to do is actually create the x sub i's. So how I'm going to do this is I'm going to go ahead and maybe I'll teach you quite a bit about Excel here. So I'm going to teach you how to I'll insert. So if you click on the column header, that A right there, and right click, you can insert a column. And then what I'm going to do, that just shifts everything over to the right, but there's a reason why I'm doing that. I'm going to do that again, actually. Insert, so I have two columns inserted. I'm going to put I here and X sub I there. Okay, these are kind of the constants in this situation. And actually even Y sub I will be a constant in this situation, so maybe I should also compute that separately as well. Whoops, moved the wrong thing over. That's okay. You can either just retype it, or you can grab it and move it over. So I'll put Y sub I. Y sub I is actually F of X sub I. There we go. And now what we're going to do is the I values are start at I equals 0, or I'm sorry, 1, and they go all the way to the end, right? But that's actually not completely true. We know that X sub 0 is going to be A, and then X sub 1 will be one step away. So I should start at that. And I'm going to go ahead and allow these to go all the way down to 50. And this is the only manual part of this. So the problem with this is that if I were to, let me get down to 50. See those numbers there tell me how far down I am. If I were to change this n to be 40, then I'd really want to decrease this list manually to 40. So that's the only piece that's a little bit of a pain. X sub I, well, this is going to equal A plus I times delta X. Now, there's a problem with this. Obviously, the very first X sub I is A, right? And the very last X sub I should be the value of B. So when I scroll down here and when I make the formula work, that should be the 8.1 pi version. However, if I were to just grab this guy and drag it down, there'd be an issue. You can see it already. It's telling me all my X values from that point forward are 0. It's actually not true. What it's doing is it's taking, like this guy right here, maybe it'd be more instructive if I went back one. So this guy right here is using I being 0, A being 1, and delta X being 0.488938. Okay. But if I go to the next one in line, because I dragged that formula down, it is actually dragging all the references down too. Well, the I is correct. That went down, but also the A went down to the next row, and so did the delta X. So it's referencing nothing here. We don't want that. We want those cell references to be static, or what we would call absolute references. So what I'm going to do is go back up to this very first one, click up here, and let's see, it was, let's see, A was this guy, the H11. I'm going to double click on that, and if you press F4, it puts little dollar signs in front of H and 11, which means that is going to be an absolute reference. It's not going to move if I drag this cell down. Same thing with the N11, which is a delta X. That's going to be always in the same position. So if I hit enter and now go over here and drag this down a little bit, you'll see that actually my X values adjust accordingly. Another thing you can do here, rather than drag that down, is you could just, as long as you have on the left-hand side here pre-filled these, you could just double-click the lower right-hand corner. Oops, because I had stuff below, it didn't do it. Let me delete that stuff and show you. So I could double-click this lower right-hand corner, and it'll pre-fill everything all the way down to the bottom where I get to 8.1 pi, which is 25.44 whatever, which is exactly right here. It's B. So that's pretty cool. Now, F evaluated at X sub I. Well, I know our function. Let me go ahead and grab our function here and move it over so you can see it. Okay, there's our function right there. So what I'm going to do with that function is I'm just going to go ahead. I cannot evaluate. That's the integral. We want to plug into the integrand. So what I'm going to do is evaluate this function equals at this X value. So I'll say equals the sine of, Excel automatically assumes you're in radians, sine of that guy, times, you can't do E here, you have to do EXP for the exponential function, which means base E raised to a power, of that x value squared. Okay. And then you hit enter and you could see that that is the function evaluated at 1. And you could test that on your calculator. And I could do the same trick, double click here, and it'll do all this down here. Now, the problem with this is that this function is terribly large. So I should probably adjust this to be maybe a little less dramatic. So let me put a negative in front of this, because that way it doesn't blow things out of proportion, which means that in this exponential piece up here, I'm going to put a negative, and then I just have to double click the lower right hand corner, and you'll see that these numbers, did I do that? I just found a flaw in Excel. That was pretty cool. Excel is reading this not using the order of operations. That is interesting. So what I'm going to do is go up here. You can see actually the formula bar here. I've already tested it out. I'm going to write as a -1 times that x value squared. A little oddity in Excel. I've never seen this type of mistake, but it is actually a mistake that Excel is doing, not me. If you right click now, you can see. There we go. Now these numbers are exceedingly small, right? They're basically 0. So I've chosen a ridiculous function to deal with here, but that's okay, right? So we're still going to go ahead and use these methods. All right, so the right endpoint method and the left endpoint method, the midpoint method, the trapezoid method, all that fun stuff. We're going to go ahead and build our Excel package to work with this. Right, and in a moment we can change our function to do something else. Okay, so here we go. The right endpoint method is actually going to be pretty easy here. I'm just going to say r sub n. That's going to be incredibly easy, because what we're going to do is add up all the function values and multiply that sum by delta x in the long run. And we're going to start at I equals 1. So we're going to actually start with these function values, add them all up, all the way to the bottom, and then multiply that result by delta x. So this will equal the sum of, and then you could just start at the first, the x sub I function, x sub 1 function value, and go all the way down until you've selected the entire column there. And then you're going to multiply this by, just have that multiplication sign up there, this value of delta x. And if I hit enter, this is the area underneath the curve approximated using right endpoints. And actually, because we're using 50 slices and so on and so forth, this is going to be pretty close to exact. Now, if I use the left endpoint method, there we go. On the left endpoint method, when I is equal to 1, we're actually using x sub 0. So this summation is going to start at x sub 0 here and go all the way to almost x sub 50, but 1 shy. Notice in this highlighting it says I have 50 rows. It's because I should have 50 things being added up. And then I'll end my parenthesis, scroll up here so you can see that. I'll hit multiply, and again, multiply that by delta x. Oh, that's very interesting, right? Well, it shouldn't be too much of too crazy of an observation, because what we've done here is using right endpoint method, we've added 0.1 to 0.01 to 0.001 and so on and so forth, all the way down to basically we're adding zeros at the very end. Left endpoint method, we actually are 0.3 greater. So that's actually a pretty significant overestimate. So now let's do the midpoint method. And the midpoint method won't be as easy, because what we're going to be doing with the midpoint method is we're going to average x values. And so we're going to need to build another row, or I should say another column, really. Now, really the only way I can think of saying this is f of x sub average, right? The average x value. Sorry, you can't see that. So what I'm going to do here is I'm going to just evaluate the function at the average of, for example, when I is equal to 1, x sub 0 plus x sub 1 divided by 2. So I'll actually start it right here. And I'm going to type in the formula. So this is going to equal my function evaluate, actually, you know what I should do is find out what the average values are. So let's go ahead and find out what the average values are first, and then find out what the function value is at those averages. So I'm typing in here the x average for that ith interval. For example, in the interval from x equals x sub 0 to x sub 1, I need the average x value. So I'm going to average those two numbers. So this is going to equal parentheses this plus this, and then divide it by 2. That'll be the average on the first interval. And now all I actually have to do is drag this down, right? And double clicking wouldn't work here. Double clicking the lower right hand corner will not work because there's nothing directly to the left to match up to, so it won't do that. And then all I'm going to do here is just evaluate the function at that value. Again, the function is just equal to sine of this x value, and then times the exponential function, evaluate at -1 times this x value squared. Okay. And let's see how this works. Now I can double click the lower right hand corner because there's a neighboring value to the left. Okay, so we get something like this. They're still horribly zeroed y values. We'll take care of that in a moment. And now looking at the midpoint method over here, it's just we're going to sum up these averaged function values, or function of average x values, and multiply the result by delta x. So in this case, m sub n is just going to equal the sum of these function values right here, and scroll up so you can see it, times this delta x value. Okay, and you can see that it's somewhere kind of in between. By the way, the midpoint method, you may have already learned this in your Calc 2 course. The midpoint method is better than the left and the right endpoint methods. Actually, it's better than the trapezoidal method too. But we'll still do the trapezoidal method. And the trapezoidal method, scroll over so we can see it. This guy right here, I'll scroll up. I'm going to use this closed form of it. We just need delta x, which I already have. We need a 2, which I can just type in. And then we'll need the function values, which we already have. And so what I'm going to do is build the actual components of it. I want f of x sub 0 and then 2 of everything else except for f of x sub n. So here's how I'm going to do this. I've already computed all the function values right in this column right here. So I just want this to be, I'm just going to say trap method here. Okay, I'm going to let this equal this function value, and this next line equal twice the next function value right here. And that's actually all I want. So if I drag this down just one, just so you can see the formula, the next one also says twice C15, and I can keep dragging down if I want. So I'm going to drag that all the way down until I get almost to the bottom, just right there. And the very last one is just going to equal the actual function value at C63 there, because again, it is going to, we're looking for the only one of the last function values and only one of the first function values, but 2 of everything else. Okay. And now I'm just going to add all of those up because again, that's what the formula is right up here. Add up all those function values and multiply by delta x over 2. So t sub n, that's going to equal the sum of all these function values that I've modified here, all these guys. Close that out. Scroll up so you can see the sum right there. And I'm going to multiply that by this delta x over 2. There we go. So the trapezoid method gives me an approximation underneath the curve, the area underneath the curve, to be a 0.13, whereas the midpoint method says a 0.12525, and so on and so forth. And now we'll go on to Simpsons Rule. Simpsons Rule is kind of nice because we have a nice working formula just like we did for the trapezoid. It's all the way over here. It's going to be a delta x over 3. That's easy enough to type in. And then we'll still have to recreate the function values, but this time the function and then 4 times the next one and 2 times the next one and 4 times the next one and 2 times the next one. So let's see if we can build that easily using the intelligent method in Excel. I'm not 100% sure it's going to work. At least I know the very first value is just going to be the first function value, f of x sub 0. The next one will be 4 equals 4 times f of x sub 1. And then the next one will be 2 times f of x sub 2. Now, we click on that cell. You can see up here it says 4 times f of x sub 1 is really what that means, and 2 times f of x sub 2. If I grab those two and drag down, there's a couple spots. Let's see if this is 4 and that's 2. It sure is. So it does drag the pattern down. 16, so on and so forth. So let's go ahead and just drag this all the way down, almost to the very end. Now remember, right before the very end, this last one right here should be a 4, and it is a 4C62, and then a 2 right before it. The very, very last one in the line should just equal the function value. There we go. All those little green arrows just means that Excel thinks we made an error, but we really have not. And so let's see, Simpsons method will give me that it's equal to the sum of those. Let's go ahead and add those up. There we go. Close that off. See up here that I did that, and multiply by, again, delta x over 3 this time. And there you go. Now that's actually a very good approximation to the area underneath the curve over this interval. Now, if you want to change your function and create a kind of a more interesting function, you could totally do that. So let's say you want to do the integral from 0 to 20 of the natural log of 1 plus e to the x. Let's still keep with 50 slices because that is just easier to deal with. I'll start with a equals 0. You'll see a lot of things about to change. Okay. And I'll end with b equals 20. See a lot of things change. And our delta x is already computed for us. There's our delta x size. We're still going to do 50 steps. The only thing I have to change here is my function, are my function values actually, because I notice, let's see, where else are my function? Yeah, we have, these are computing function values here. So in row column J, everything else is actually fine. So let's go ahead and change the function values. The function is going to be, let me go ahead and write equals, log, log is the natural log. And then, because ln doesn't work. If you try, oh, returns natural logarithm of the number. Maybe I should try that. Let me do that. Natural log of, let's say, exponential of 1. Let's just see what happens. Okay, that does work. All right, so I thought log was the natural log in Excel, but it's not. All right, so natural log of 1 plus e x raised to the, and then we click the x value. Boom, boom, and hit enter. And now I'm just going to double click this so it goes all the way down to fill in all that stuff. Okay. And the right endpoint method is automatically computed properly. The left endpoint method is automatically computed properly. Actually, the trapezoidal method is computed properly as well, and so is Simpsons Rule. And notice trapezoid and Simpsons Rule are very close to each other. The only one that actually is not computed properly is the midpoint method, because we need to rewrite the function there too. So I'm just going to type ln of 1 plus exponential of the averaged x value. And then close, close, enter, and then double click to go all the way down on this one. Okay, and you'll see, there we go. There's our approximation, 200, 200, 200. And the best of these is going to be the Simpsons method. You can adjust, like I said, you can adjust n if you want to adjust n to be, let's just do 20 here. All right, and so basically our step size is 1. Well, if you do that, you're going to have to adjust quite a bit of your data too. So if you do that, I'm just going to delete these down here just for your information. So hit right click and click delete. And then the regular x values and the function values are perfectly fine. The right endpoint method goes to C33, which is right down there. You can click on this and see what the right endpoint method does. And the left endpoint method actually is doing the right thing as well, or the correct thing as well. Actually, it's not. So we're going to adjust that to end at 32. There we go. So left endpoint method is still properly adjusted now. These x values are still working fine. These are still working fine. Yeah, they are. The trapezoid method will not be the same. Okay, because remember, the trapezoid method starts with 1 of the first, 2 of everything else, and then only 1 of the last. So I have to change that to a 1 right there. Okay. And then finally, Simpsons rule, again, starts with 1 of the function value, then 4, then 2, then 4, then 2, and so on and so forth. Notice this last guy right before the very last one is a 4. I have to change that 2 to a 1. There you go. And again, actually really good approximations. So we've seen that's 200.8225 is what we think it is. Notice the right endpoint and left endpoint methods give pretty bad approximations. But what if instead of 20 slices, we did 8? Okay, so now I'm just going to delete everything before 8 just to showcase something here. Delete. Again, the right endpoint method, you can see it's doing the right endpoints there. The left endpoint method is almost correct, except it shouldn't do that last endpoint. So there we go. The midpoint method is actually doing the right thing. It's adding up all those function values. The trapezoid method is almost doing the right thing, except for this last one has to have only 1 of them. And the Simpsons rule is doing the right thing, except for the last one has to have only 1 of them. Now notice, remember, it was supposed to be 200.8225 or something like that. Still, Simpsons method is at 200.8 close, right? Everything else is starting to veer off. But with 8 slices, that's pretty good. 8 slices over an interval from 0 to 20, that's pretty awesome approximation. Now, let's do 4. I just want to see how good Simpsons is. So here we go. Deleting everything else. All right. Again, left endpoint is going to have to be modified because it's going too far. So there we go. And now remember, it's supposed to be 210.225 or some 200.8225 or something like that. You can see the midpoint method actually still is 200, so it's only off by a half. That's pretty good. Trapezoid method just needs a simple little adjustment here again. Trapezoid method's off by about 1. And Simpsons rule, once I make that adjustment, is off by about 0.4, still better than the midpoint rule. So not bad. That's pretty good. With 4 slices, that's pretty amazing. Well, the reason why is because natural logs are very slow growing. Anyhow, you could have probably stopped watching this a long time ago.